Hello, and thank you for joining me for this session of the conference. In the next 20 minutes, I want to cover side channel attacks in a way that makes them understandable to everyone, trying to be simple without being simplistic. So, apologies to those of you who have degrees in maths and physics. I hope to show you why side channel attacks matter for IoT devices. So what will we cover? I'll cover the physics involved without the heavy maths. I'll do the cryptography without the heavy maths. We'll look at ways of collecting leaking data and touch on how unauthorized access can be escalated. And we'll make suggestions about gaining greater security. But first, the physics without the maths. When electrons move as electricity, they lose energy as heat and electromagnetic waves. Engineers try to maximize and minimize these two features depending on what they want. Push for the heating effect and we get electric heaters, hobs and ovens, soldering irons and arc welding. Push for radiation and we get radio and radar supporting our mobile phone networks. And here I want you to note that the moving electricity generates the radio wave which is picked up by an aerial in which it creates a corresponding electrical signal. There's a back and forth. Moving electricity leads to some electromagnetic radiation which can generate electricity in wires. Push for more magnetism and we get motors. Push for moving magnetic fields and we get dynamos and alternators. The latter generate a large proportion of the world's electrical power. That's the alternators, not as yet wind turbines. But you can't get one without some of the others, and we shall come back to this. Now for the cryptography without the heavy maths. And let's start with Kirchhoff's principle. A crypto system should be secure even if everything about the system except the key is public knowledge. No hiding stuff away, no trying to keep it all secret. Everything should be out there except the key. Ideally, the encrypted file should give no indication of what the plain file is about. And when I say ideal, it takes a file like this and gives you this. Or a file like this gives you this. And indeed a file like this and gives you this. And decrypting has the same. Looks boring, gives you a file. Looks boring, gives you a file. Looks boring, gives you a file. So how does the encryption work? I'll deal with one example. Here is a diagram about how AES, the Advanced Encryption Standard, encrypts and decrypts. Although it looks like a linear process, top to bottom, the middle bit repeats. As you can see with the pink boxes, there is reference to repeating rounds. And in the next slide, I'm sorry it's a bit blurry, you can get a better idea of what goes on in the repeated rounds. They're here again in pink. Chunks of plain text drop in at the top left and go round and round clockwise through the steps being worked on by the mathematics until they drop out bottom left for a special last round. That going round and round generates rhythmical patterns in electricity consumption and electromagnetic radiation. Rhythmical patterns. We'll come back to that idea again. But before we marry cryptography with the practicalities of actually encrypting and the physics that leads to vulnerabilities, let's take a look at Tempest. Tempest was a code name for the telecommunications electronics materials protected from emanating spurious emissions. I picked this paper, which was declassified in September 2007, and discusses events in the 1940s to 1964. It talks about compromising radiations. During World War II, Bell Labs, which provided encryption machinery to the US military, realized that their equipment leaked information. They told the military, who were taken aback and said, "Prove it!" So they did. They set up in Varick Street, New York, just across the road from the Military Encryption Center, recorded for about an hour, and in 3 or 4 hours had accurately decrypted about 75% of the plain text. We've moved on from electrical to electronic and use considerably less electricity these days. But we still use some, and it moves and works, and it is possible to follow power consumption and pick up associated magnetic waves. Much of Tempest is still classified, or if published, heavily redacted. But this document from 1995, released in 2007, gives guidance about installing cryptographic equipment, red stuff, near ordinary cables and equipment, black stuff. Depending on the seriousness of the cryptographic red equipment, it must be 0.5 meter to 1 meter away from any black wires, and any red wires carrying cryptographic data must be at least 5 centimeters away from any black wires. So we still have the physics that moving electricity generates an electromagnetic field that can then cause electricity in a wire. We're all probably familiar with a well-known app referring to end-to-end encryption, and once the plain text has been encrypted, like the photographs I showed you earlier, they are safe from snoopers unravelling them even if the snoopers intercept their transmission. However, there is an unsafe side. Unauthorized access to plain text before encryption or after decryption is a problem. The acts of encryption and decryption leak data, as shown here with the little arrows, and these leaks can be harvested, analysed, and the encryption keys obtained. The leaked data holds clues to the rhythmical patterns I mentioned earlier. So let's look at these ways of harvesting data. This is the first of 3 papers from Erin Tromer's team. Here you can see a laptop on the right with its power supply, 10 meters of Ethernet cable, and their harvesting setup of a crocodile clip and a phone. This is shown in a bit more detail. The crocodile clip just clips onto the cable. 10 meters from the laptop. It could be on the floor above or the floor below, in another office or apartment, or in a services cupboard. The setup picks up power consumption data for each processing step in the laptop, and Tromer's team gained RSA and El Magal encryption keys from the laptop. It's an example of an attack where the side channel uses leaked power consumption data. What else is there? At the RSA conference in 2012, Gary Kenworthy, seen here, of cryptography research, demonstrated collecting encryption data from the phone in his hands from about 10 feet away from an antenna on the right-hand side. He's quoted in the article saying, "This antenna is not supposed to work at this frequency, and it's been in someone's attic for years and is a bit bent. You could build an antenna into the side of a van to increase your gain. Well, now you've gone from 10 feet to 300 feet. That's a long way." And this looking for electromagnetic fields, I follow up with the second paper from Erin Tromer's team. Here you can see a recording and analysis laptop to the right, the target laptop to the left, and a coil 0.5 meter away to collect the electromagnetic waves. The team realised that they could make the setup just to collect data, and came up with the Portable Instrument for Trace Acquisition, PITA, and it is about the size of a pita bread, as you can see it sitting there. You could hide the device in your lunch if you're an attacker and sneak the device into a target building. Their PITA was Wi-Fi enabled and could either store the harvested data or, using the Wi-Fi, have it analysed in real time. In order to avoid the expense of a software-defined radio, they found that they could use a cheap AM radio and combine that with a mobile phone for data storage. They did have many problems to address, but they got the encryption keys they were looking for. So those are examples of harvesting data on electrical power use or associated electromagnetic waves. But there is another channel leaking data that can be harvested. Finding the keys using sound. After lots of experimentation, they had this setup of a recording device in the case and a parabolic microphone on the stand and a laptop 4 meters away at the right-hand end of the picture. This distance could be increased to 10 meters with human input to fine-tune analysis. They conjecture that the laser microphones and vibrometers will greatly increase range if there is a direct line of sight. And at the other end of the scale, they found it was possible to gain keys on certain target computers simply by placing a phone's mic near the fan exhaust. All the attacker needs is to download a suitable app to the phone. Once a side-channel attacker has the encryption keys for an IoT device, they can imitate it on the network, they can load malware to it, they can escalate privileges vertically and horizontally as they exploit vulnerabilities in a network. Think of all the IoT hacks you know about. They probably could be available via a side-channel attack. After all, security is only as strong as its weakest link. While I suspect that most of you, if not all of you, know of this work, it shows how a side-channel attack extracted a global encryption key from one device and used it to bypass authentication of new firmware on many related devices. It meant that a large multinational company's cryptographic techniques to protect a major product failed. It's a fascinating paper of how they made a rogue smart light bulb and how they used it to infect other light bulbs with a worm. Those light bulbs went on to infect other light bulbs with the worm. They discuss how the idea could be used to switch on or off all the smart light bulbs in Paris, or permanently brick them, that is, make them no longer work. So that was a fairly speedy overview of side-channel attacks. So what can be done to resist them? The physics remains the same. If we can reduce the amount of electricity moving around, we reduce the power consumption and both the associated electromagnetic waves and sounds. A smaller target signal may be harder to read if the signals all around it stay undiminished. So it's a bit like trying to whisper so as not to be overheard, but that doesn't always work. There are things called Faraday cages, and they can be good for electrostatic fields, but need to be carefully tailored in terms of materials, their overall size of holes in the cage for both weight reduction and air circulation, that is, so that heat from the working devices can be expelled, for example, by a fan. Faraday cages are less effective on limiting the magnetic part of the electromagnetic fields, but the physics is complex. I have heard people refer to trusted execution environments. Do they help? Well, if we look at this paper from 2017 by Ronan Lachermes and his associates, they attacked a trusted execution environment on a Raspberry Pi and succeeded. They quite rightly confirmed that ARM's Trust Zone is only advertised as a software security solution, not hardware. Lachermes' team state that critical applications in Trust Zone are no more secure than in the normal world with respect to electromagnetic analysis via side-channel attacks. So what else can you do? Use NIST, the US National Institute of Standards and Technology. They have this vulnerability database so you can check if components being suggested by a supplier have any outstanding vulnerabilities that would put your customers at risk. The database covers software and hardware vulnerabilities. It's simple to access, free to use, and kept up to date. You can also get in touch with the likes of pen test partners about possible vulnerabilities in your offering before you launch it. After all, an ounce of prevention is worth a pound of cure, but in terms of reputation and possible legal action, this makes a great deal of sense. I'm looking forward to Thursday when Ken Monroe, a partner of Pen Test Partners, will be talking about how IoT is littered with security disasters and what can be done. Finally, we are left with software approaches. Here is a power consumption trace of 10 rounds of a normal AES on an oscilloscope. As you can see, there is a rhythmical pattern. By using another 100 to 200 traces like this, it would be possible to determine the encryption key used. The software goal is to break up that pattern. There are many software approaches, and most carry heavy performance penalties. Some are even 100 times slower. Some software approaches with performance penalties of 10 to 15 have been shown to reveal the encryption key with under 1,000 traces. But it is possible to break up the pattern with much lower performance penalty of about 2.5, and in a way that cannot be circumvented by reverse engineering. It's also extremely resistant to being broken. So in sum, how can we reduce vulnerability to side channel attacks when the physics remains the same? Reduce power consumption to the processor? It helps, but doesn't solve the problem. Provide Faraday cages. They help, but they don't solve the problem. Trusted execution environments? They're a bit of a red herring. So check your software and hardware components for vulnerabilities and use NIST and/or testers like pen test partners. And seek encryption software that totally disrupt the rhythmical patterns, so we change the algorithms so they can't be read. Thank you for listening.